Welcome back to Module 26 of Engineering Vibrations and Introduction to Single Degree of Freedom Systems. The exciting thing is today's learning outcome is that we're going to solve for the response solution of a simple single degree of freedom system of a real-world modeled system undergoing free underdamped vibration. Here's where we left off last module. We had the response solution and we had put the differential equation motion in standard form where the coefficient of the acceleration term is equal to 1 or unity. And the real world example I want to look at is this U.S. Air Force photo where we have these tanks, fuel tanks, wingtip fuel tanks. And so this is a model, this could be a model of the fuel tanks here with the cantilever beam spring action of the wing and damping action, taking out energy. And this is a Northrop F-89 Scorpion aircraft. And we're looking at the vertical motion up and down as this airplane or aircraft operates, the vertical motion of these wingtip fuel tanks. I give you the differential equation of motion for that system that we would come up with. This is just some values that I've put in. And let's say that we give the wingtip fuel tanks initial conditions of an initial displacement of 0.4 meters up and an initial velocity of 0.2 meters per second up. And what I ask you to do is to determine the damping ratio and the response solution. And so the first thing I'm going to do is put my differential equation of motion that I'm given in standard form. So I've divided the differential equation of motion that was given by 2 to make the coefficient of the acceleration term equal to 1. Therefore, I can easily identify that the coefficient in front of the velocity term is 2 zeta omega natural, and the coefficient in front of the displacement term, or the y term, is equal to omega natural squared. Therefore, omega natural squared being 25 gives us immediately the natural frequency of 5 radians per second. And setting 2 zeta omega natural equal to the coefficient 4 gives us, we also know that omega natural now is 5. That gives us zeta as being 0.4. And so we're easily able to come up with those values. And so that's the first answer. The damping ratio, zeta, is equal to 0.4. Now we want to go on and find the response solution. Well, I've got many of the values now. I've got omega natural times zeta is 0.2. That's 5 times 0.4. I'm given the initial displacement of 0.4. I can find the damped natural frequency, omega d. Omega natural was 5. I have to subtract out 1, or multiply that by the square root of 1 minus zeta squared. Zeta was 0.4. And so we see that the damped natural frequency is 4.58, which is expected to be less than the natural frequency. I can substitute that in. And the quantity in front of the sign term, I've put in all the values that I'm given. It's 0.218 when I multiply those out. And so there is my response solution with actual numbers given for this situation. And so I could plot that out and see the actual motion of the wing tip fuel tanks. So as a summary, this was a nice real-world example of solving for the transient response solution of a single degree of freedom system undergoing free underdamped vibration. And that ends this module.